Alright, the next application. So we have a carpenter who makes two different size tables. He's determined his profit equation, given by that P equation, where X represents small tables he creates and Y represents large tables. He wants to optimize, maximize profit, but he's limited to a certain budget. Alright, each small table costs him $100 in materials, and each large table costs him $200 in materials. He has $16,500 for his budget, right? Which means he can spend up to that or less. So that's the constraint part. Now this one's a little more complicated than the last example because we have these extra numbers here. So remember, if we make X tables that are small, it costs $100 each. Y large tables cost $200 each, and he can spend $1,600. So the constraint is 100 times X, 200 times Y, is equal to or less than 16,500. Again, we write equal to, but technically it's equal to or less than. I can't remember if it's this example or the next example where we will actually use the less than case. So when we go to set it up, remember we actually rewrite this where we set it equal to 0, so we move that 16,000 to the other side. Oops, 16,000, too many zeros. Alright, so we set up our Lagrange equation in order to optimize, so we write the profit function first. So again, be careful when writing it out, so not to make any errors. Again, these are just fairly large functions, so it's just always a good idea to kind of double check to make sure. Right, I got everything in the profit function. Now it's minus the lambda variable times that constraint equation, where we've set it equal to 0. See if I can squeeze it in on the edge of my page here. I did. Alright, so there's the constraint equation, and then we find the partial derivative, set them equal to 0, and solve. And this one is going to be linear, and again, most of them are. 8 out of 10 are, 2 out of 10 will not be. Alright, so the first order derivative with respect to x, so I take the derivative of the profit with respect to x, so I get negative 2x plus 25 plus y, zeros out, zeros out, zeros out, minus lambda times the derivative of lambda in terms of x, so we've got 100x, so that derivative in terms of x is 100, lambda. Set it equal to 0 so I don't forget. Now the derivative with respect to y, so again I take the derivative of the profit with respect to y, that's 0, 0, zeros. I get negative 135 minus 0.8y. Oh, I forgot my xy. That's the derivative of that one. Derivative of xy, right? So I get x minus 135 minus 0.8y minus lambda times 200, right? Because it's 200y. Set it equal to 0. And then remember, the lambda is negative 1 times the constraint part. Alright, it is linear, so I can set it up with a matrix. So remember, matrix, you have x, y, lambda, and then move any constant over if I need to. And I do need to move constants over in this case. I've got constants in all three equations that I'm going to have to move to the other side. So the first equation, I have negative 2x plus y minus 100 lambda equals, well, I've got to move that 25 over. So it's going to become negative 25. Second equation, I have x. This 135 is going to be moved over. Negative 0.8y minus 200 lambda equals positive 135, right? Because I add the 135. And then the last one's always the constraint. So 100x plus 200y equals 16,500. And I keep adding an extra 0 here. 16,500. And so there's my 3x4 matrix. So again, just make sure you're careful when you type it out. The most common mistake students make is forgetting to move the constant over and making it the opposite sign. Alright, so if I've carefully placed those in my matrix, I do my row reduced echelon form, I should get the matrix with the diagonal of 1s and 0s and then numbers, so that comes out 65, 50, negative 0.55. Alright, so that's my x, that's my y, and again, that's my lambda. I found it. We don't do anything with it. We just use it as part of the application. Alright, so my x is 65, my y is 50, and so those represent my large and small tables. Alright, so they can make 65 small and 50 large tables. To maximize profits at, well, you got to put that 65 and 50 back in the profit equation. All right, go all the way back up into, not that one, you go all the way back up to the one given in the problem. You plug it in here, and again, just make sure you're very careful when you plug in your 50 and your 65. I get that it comes out 1,400 is the optimum profit. Alright, so that means the next one's going to be the case where I'll have a less than case. This is another one that's not too bad. Alright, we'll stop there. I'll pick up the next example in the next video.